So, welcome everyone. Welcome to the IEP seminar for this week. The speaker is Giancarlo Ghirlanda from Brera Observatory. Brera is close to Milano. Giancarlo spent the week at IEP. We had many very interesting discussions. I hope that Giancarlo enjoys this week.
Definitely.
As we did. So Giancarlo is a senior member of the high energy group at the Brera Observatory, and this is a group which is extremely active, very productive. They have contributed to practically all aspects of GRB physics, the front emission, the afterglow, the associated kilonova. They perform population studies, and they have been extremely active very recently after the discovery of the first electromagnetic counterpart to gravitational wave events, the famous events which happened on the 17th of August 2017. So describing all the contribution of Giancarlo will take a very long time, and I will not do it because it could be very long. We did many different things. But I want just to say that the group in Brera are really be at the forefront of the European effort after this August 17 event, with I mean, many very important papers which attracted a very large audience. And what is also very extraordinary with Giancarlo is that he is not only a theoretical astrophysicist, he is also very much involved in observation, and he especially led the European VLBI effort to follow the radio afterglow of this August 17 event. And it is really not so common to have someone who is at the same time a very strong theoretical astrophysicist and who can lead a very large international cooperation. So, as I understand, in today's seminar, Giancarlo will discuss many different topics in GRB physics. There is no special order. It will be different issues in GRB physics. And in French, we call it a potpourri. So it will be a sort of potpourri of GRB science. So Giancarlo, please.
Yes. So thank you. Thank you for this very nice introduction, Robert. Let me thank you, all of you, for being here, and Robert, Frederic, Irina, for organizing this visit here. It was really a pleasant week. We had many occasions to discuss, and it was very stimulating, especially after the last 2 years, I would say. So indeed, this is a kind of potpourri, but an ordered one, because during this seminar, I would like to take a kind of journey from the very high redshift universe going to the close-by universe, using gamma ray burst as a kind of guide along this journey. So these are the 4 parts I will try to cover. Of course, given the time, provided I can stay within the allowed time, I will not have time to go very deeply in these topics, but just give you some flavor of what I think is relevant. So let me start with a brief introduction, which is a kind of indeed journey across time since the discovery of GRBs back in the 70s, nearly 50 years ago. They were discovered serendipitously as flashes of gamma rays. In the 90s, as you probably know, we acquired a lot of events demonstrating the fact that they are distributed isotropically in the sky. This was the first hint of their possible extragalactic origin, which was confirmed starting in 1997 with the pinpointing of their afterglow emission, which allowed to acquire spectra and measure their redshift. Soon after, in 1998, we had the first evidence that these sources, at least the long ones, are associated with the core collapse of very massive stars, with the association of the first supernova event and many others coming in the years later. 2005 was a brilliant year because it was opened with the launch of the Swift satellite, which unveiled several properties of these sources, especially in the X-rays, but most of all, it is a machine for measuring the distances of these sources, allowing us to study their intrinsic properties. The story goes on because in 2008, there was the launch of the Fermi satellite, which assessed the emission of these sources at high energies. MEV up to GeV energies, which is very important because it allows to probe the most extreme phenomena happening in these sources pertaining the acceleration of particles and the corresponding emission. Then, as anticipated by Roberta in the introduction, 2017 is well known to you as the year when we had the first electromagnetic counterparts to a gravitational wave event produced by the merger of two neutron stars. In this case, GRBs already played a major role. This was evidence of the fact that the short population of GRBs is indeed related to the merger of compact objects. Still one event, and more to come in the next years. Last but not least, in 2019, another important opening of a window, of an observational window on these sources came with eventually the detection of the emission of GRBs at very high energies, up to TeV energies, which is indeed extremely important because it's a further way of proving the physics of GRBs in the extreme environment where the particles are accelerated, as well as use them probably with the acquisition of new events to characterize the properties of the extragalactic background. Okay, I pretend, forgive me if this is a bit too crowded, to now give you with this handmade drawing a flavor of what is a gamma ray burst. Now, we are quite confident that there are at least two channels, which are the progenitors, which can lead to gamma ray burst. For the short ones, we think there should be a binary system hosting at least one neutron star. For the long ones, we believe that a major player is the presence of a massive star. In both cases, the formation of a collapsed compact object with possibly high rotation surrounded by some disk should be able to power a jet, which at the base, close to the compact object, is energized and has to travel through the environment which it has in front of it, which is respectively the merger ejecta and the standard envelope. If the jet has enough energy to travel through this environment, close by environment, it eventually breaks out of this environment and it produces a successful jet, which is the condition to have a GRB as we observe it. In this travel, the jet acquires a structure in the sense that its energy is probably concentrated in a narrow core where you have the bulk of the energy, most of the energy, and a large bulk velocity, and then some material around that, surrounding this core, which attains lower velocities and contains a little bit more less energy. Dissipation of energy at some distances is producing what we call the prompt emission, gamma rays, and the deceleration of the jet in the interstellar medium is producing the afterglow. One key ingredient of this scheme is the fact that in gamma ray burst, we have relativistic jets. Therefore, you can already understand that what we observe is intimately related on the one side on intrinsic properties of the source, on the other side on the way we see it, I mean, the angle under which we observe the source, so the orientation of the jet. And this will come up during the presentation again. Now, we are used to call gamma ray bursts and to divide them into two classes, long and short. This division historically was made by taking roughly a 2-second separation between the two classes. I must say that this division probably is more complex than that. Also, if probably you heard about this event for which there were 4 papers appearing in the last couple of weeks, which probably should force us to rethink about this separation. But if we take it for granted, you see from this, can I get a stick or a pointer probably? However, if you look to this plot here, you see, if it's not it's much problem. No, okay, Irina, don't worry. I will just. Yes, perfect. Thank you, Irina. So you can see from this graph here that the detection rate of GRBs is quite large. different instruments are providing different rates. This is an important point because it tells you that we are subject to selection effects. And also, if you look to the short and long fraction is also different according to the detector, which is used, which is detecting these sources. And
can you cut the sound on your computer because there is an echo?
I can't. Yeah, I can't. It's
yeah.
Like this.
I think we should more than that.
It's okay now. Oh, it's coming. Oops. Okay, so an important point is that if we go to see how many bursts we detect for which we measure the redshift, we have an efficiency which is provided by Swift mainly, which is about 1/3 with a redshift measurement. Now this is just to say that what we observe and what we detect is the tip of a larger iceberg. And the aim of the studies which try to treat gamma ray bursts as a population want to reconstruct instead what is not observed. This is the first part of this talk, which I'd like now to deepen a bit. In this plot, you see the energy as a function of redshift. This is a collection of long gamma ray bursts. The highlighted one were observed with X-shooter, which provides high resolution spectroscopy, accessing some interesting properties of the environment close and on larger scale of the host. What is important here is that, as you can imagine, describing the properties of these sources as a population at the first stage concerns the fact that you want to reconstruct or describe how they are distributed along the Y and the X-axis. For instance, in the X-axis already with this observed sample, you can see from the histogram that the shape of their distribution as a function of redshift is indeed reminiscent of their origin related to stars and the distribution of stars as a function of redshift. There are different methods we can use to build up these two population properties. The two leading ones are direct inversion methods, where you basically play with graphs like these and you, let's say, perform some statistical analysis trying to remove or account as much as possible as you can for the selection effect that you have in this kind of distribution, or indirect parametric methods, which instead rely on the fact that you make some functional or theoretical hypothesis on the, let's say, distribution they should have all over this plane. You apply at your best knowledge the selection biases and you try to match what you observe. I hope I gave you the flavor. What is interesting is that the results of these methods, which sometimes are a bit in tension, can be at the end also compared with theoretical models. I will try to show you the results, of course, with this slide, which is a bit crowded, where you see the results for the luminosity function. So here you see most updated, I would say, results for the luminosity function of short GRBs and long ones. First of all, you see there are common features. In both cases, we have a wide distribution of luminosities, which ranges from low luminosities up to very large luminosities. Another common feature is that at high luminosities, the luminosity function of long and short GRBs tend to, let's say, agree when you compare different results, which are represented in these plots by green, violet, and red line. The observational results, I mean, the luminosity function derived through the observations are represented in this plot by the green line and by the violet line. The red line is a model, a purely theoretical model, which is built this way. As I said before, we think GRBs have a jet, a relativistic jet, and therefore the number of events as well as their luminosity depends on the orientation of the jet. Intuitively, the larger is the viewing angle, the dimmer, the lower is the luminosity, but the larger is the number of sources because of random orientation in the plane of the sky. And this is the reason why you have this large increase of the number of sources at low luminosities, both for long and short GRBs. As you can see, there is a kind of tension between theoretical predictions and models in the low energy part, whereas they agree at high luminosities, both for long and short GRBs. Now, the bottom line here is that for short GRBs, we have, in a way, at the moment, a kind of wall, which is represented by the gray region here, which is the rate of binary systems that we derive from gravitational wave detections, in the sense that we cannot overproduce, at least if this is the only channel, let's say, this line here. In turn, this constrains some properties of the jet. I will say this in the next slide. On the long gamma reversed side, you see there is this bump in the theoretical predictions with respect to what is observed in a way, which is not inconsistent with the fact that in this region we have some lower limits because of incompleteness. And this bump is determined by different, let's say, parameters of the simulations, but the leading one seems to be the fact that in order to derive this curve, you have to simulate a jet from the, they tried to simulate a jet from the base, okay, when it is injected, the energy, where it is injected, the energy that travels to the environment, to the material of the star. So the smaller is the base of the angle, and let's say, it seems that the jet, when arrives at the surface of the star, acquires a sharper structure. It is more collimated, and the distribution of the energy in the angle is sharper. And this makes the appearance of this bump here. In general, reducing the base of the jet injection region seems to bring this curve down here. So this is informative to say as a bottom line on the jet structure. So the luminosity function shape is indeed a tool to study the structure of jets in GRBs. And this was presented in some works by two PhD students back in 2015 and 16. Let's go to the rate now. This is the cosmic rate derived with these indirect methods. This is for short GRBs. The first consideration we can do is that if you take the cosmic star formation rate, which is represented by this dashed blue line, you see that there is let's say, difference in the peak. Short GRBs peak at lower redshift with respect to the peak of the cosmic star formation rate. At first value, this difference tells you something indeed about their progenitors and can be used, with some works has been used, to infer the properties of the distribution of the delay times, because indeed this shift is due to the fact that you have to wait some time between the formation of the binary, its evolution, and its merger, okay? And so you have a delayed peak of the GRB formation rate when the two systems merge with respect to when they form. And this can indeed provide information about the minimum time scale, the distribution of the scale, the shape of the distribution of the time scale of the delay time. Another interesting thing we can learn from this plot is that if we take the observed rate with its uncertainty, for instance, and we correct for the opening angle, we arrive to the local intrinsic rate of short GRBs, which indeed can be compared with the rate of binary neutron-star merger derived from gravitational waves, and the ratio of these tells you what is the fraction or minimal fraction of burst of binary mergers, which are able to produce a jet, which is able to successfully penetrate the environment and explode out of the star. So it's very informative also, this kind of comparison. Let's go now to long gamma reverse rate. So I described luminosity function, short GRB formation rate. Now we move to long GRB formation rate. I show you some results in a recent work that we did, that I did with Ruben. It's very nicely similar to the results that were obtained by Jesse and Frederic in 2020. So what we obtain here is the intrinsic rate, because we account also for the jet properties of the population of GRBs as a function of redshift, which is represented by the red line plus its statistical uncertainty, 1 sigma. It is here compared with the cosmic star formation rate, which is the blue line, and contrary to short GRBs, now you see that there is the opposite effect in terms of peak. The peak of the GRB formation rate is at larger redshift with respect to the peak of the cosmic star formation rate. The reason for this will come in the next slide. But the interesting other feature is that at high redshift, we find a GRB formation rate, which is perfectly similar in terms of slope to the cosmic star formation rate. When we take the ratio of these two curves, which is represented here, this tells you that there is a kind of evolution in the efficiency of producing long gamma ray bursts. It is lower in the local universe, and it increases going to higher redshifts. Interestingly, if we take the ratio of the local GRB formation rate with respect to supernovae type 1c broad line rate, because these are thought to be the progenitors of GRBs, we get that there is an efficiency, let's say, in this case, similarly to short GRBs of this system to produce a jet which successfully gets out of the stellar envelope of about 1/3% of supernovae broad line producing a successful jet. So what is the reason? The most important, I think one of the most interesting features here is the fact that at low redshift, as you can see, the GRB formation rate decays going towards the local universe more rapidly than the cosmic star formation rate. The reason for this is well known since many years, but we had the opportunity to test with this result. So what we did, we built up a toy model for the mass metallicity redshift evolution by combining the star formation stellar mass function, the galaxy mass function, and the mass metallicity relation. And what we did was to derive, let's say, the, if you want, fraction of star formation happening in galaxies below a certain metallicity cut, which was the free parameter of this game. And we derived a, let's say, metallicity, maximum metallicity of host up to which you can form reliably a long gamma ray burst, which is lower than 8.6. If we apply then this toy model in terms of cosmic star formation rate, we get indeed a nice match with the dashed blue line. As a counter test of this result, we collected the results of the host mass measurements by Susanna and Jesse in these two papers, which are presented by the points here, and confronted with this toy model with this metallicity cut, we get a nice agreement. Interestingly, this red line is the model which instead assumes that long gamma ray bursts follow the cosmic star formation rate, which I can imagine now you are convinced that is not accepted, and indeed it's completely excluded already also by mass measurements. Now, since we have understood and we knew that the metallicity is the driving parameter, the next question we would like to explore now is what is the intimate role, if we go to a, let's say, smaller scale, between the metallicity and the properties of the host, of the progenitor. And this is something we are trying to work on now because naively, you understand that since the metallicity decreases going to higher redshift, therefore providing an increase of the efficiency in producing long gamma ray bursts. But we would like to understand what is the intimate relation of the metallicity with the properties, for instance, of the stellar population from which gamma ray bursts form, their progenitors form. And let's say at first level, at a lower metallicity, you might imagine that the clump from where stars are formed is more massive, and therefore you form larger massive stars. Therefore, there should be an effect on the IMF, which should flatten going to higher redshift, as well as the other competing channel for long GRBs, which is binary systems, should also quench down a bit. The other effect is more intimately on the progenitor final stages, because at lower metallicity, you have that during the evolution of the massive star, you lose less mass, and therefore you bring away less angular momentum, therefore keeping a highly rotating system when it collapses, which is a nice ingredient to extract a larger energy, through, for instance, through the Blandford-Knight mechanism from the system. So this is a work in progress. Let me then briefly try to start with these last three topics that goes from the very high redshift universe to the local universe. I don't have much to say about the high redshift universe, just it's a kind of advertisement of the fact that if we look to the GRBs we have detected, let's say a redshift larger than 6, first of all, there are not that many differences from what concern their low redshift siblings. Here you see a plot showing the prompt emission properties. Here are highlighted these events, which are now, I think, 8, the blue points, and you see they have similar prompt emission properties. And if you take a journey in terms of redshift going up to some of the high redshift events, you see that also the afterglow emission, this is the X-ray one, is in general similar to the low redshift events, both in terms of features, which are quite complex and other stuff. The only possibility which has been claimed is that when you compare high redshift GRBs to low redshift ones, it seems that they might have a smaller opening angle of their jet, which to me, and we discussed also this week, is at the moment still not a solid statistical evidence, and there are counterexamples, but it's an intriguing possibility because it could be related to the argument we were doing before about, again, something related to the metallicity of the evolution, if you want, of the properties of the progenitor as a function of redshift. What can we do with high redshift GRBs? Many things. I don't have time to go through all of them. I just want to highlight one, which is mostly theoretical at this stage, which is the possibility to unveil through GRBs their highest redshift progenitors, where you could have a transition to first stars, population 3 stars, provided they can indeed launch a jet which successfully breaks out of the star, they should produce a GRB. There are many studies that try to identify the key properties of these high redshift GRBs. Here I show you, for instance, a study where they try to, let's say, simulate how, let's say, featureless spectrum of the GRB absorbed by the environment produces 21 centimeter lines, which are in this case observed in this simulation with LOFAR and SKA with quite long exposure. This is one way. There is also the way to combine the spectroscopy with some key features of the prompt emission. I think we are trying to prepare or to explore different ways, which probably will success in combining different observations. But at the moment, we don't have any key evidence of this possibility. The other possibility is that of, for instance, studying through GRBs the metallicity evolution. This is a simulation where the mass metallicity is extended at higher redshifts here, and the simulation is done for 2 different low, faint, and slope of the galaxy mass of the galaxy luminosity function. This is done for Theseus, which was a mission proposed indeed to explore the high redshift universe with GRBs. The bottom line I want to do here is that in general, these kind of studies, as well as the others, are very promising. We need a larger statistics. And this is a concept which in terms of instrumental properties can be acquired if we build or we think about changing the current situation in terms of instruments, thinking about, let's say, a detector, which is operating at a softer energy band, because of course you have the higher redshift, which shifts the emission of these sources at softer energies, but at the same time, which is more sensitive, because indeed, due to the higher redshift and some intrinsic properties of the population of GRBs, according to simulation, the high redshift bulk of the events in the observational plane here, relating the prompt emission peak of the SED and the flux should be quite dim. This was something which has been started to do. I think with SVOM, there will be a few more cases of detections of GRBs at redshift larger than 6. 2 mission designs that were proposed, Theseus for the N5 call of ESA and Gamma of Explorer for the NASA MIDEX call, are indeed designed to, let's say, boost the number of events you can detect at high redshift, with a detection rate expected of the order of tens of events per year at redshift larger than 6. For which, for the configuration of these instruments, also on board, due to the presence of an infrared telescope, you can acquire the redshift. And so you have, after, let's say, a few hours the evidence of the detection and redshift measurement of the source, from where you can start the interesting studies that you may want to do. Let's move now to the intermediate redshift. Now here is where we detect several GRBs, and therefore we can do many studies, mainly pertaining to their physics, exploiting the statistical large number of events. There are many possibilities of topics we can cover. I decided to choose one, which is common to many of you in the audience, which is related to still a major question we have about what is the origin of the prompt emission, of the gamma ray emission of these sources. We don't know it. We have been trying to solve this puzzle for years. The argument is the following. When you observe the prompt emission of a GRB, you have the indication from the light curve that it is highly variable. Variability time scale, represented here as a function of time, shows that short GRBs and long ones have variability time scale of the order of 10, 100 milliseconds. If you transform this into a characteristic distance of the region where photons are produced from the central engine, you end up with a relatively small radius, okay? Where, by the way, a luminosity comparable to the one that you measure should be released. On the other side, if you take an SEV of a typical GRB, you see that it is a broadband non-thermal spectrum peaking at 1 MeV. And these two, let's say, elements put together suggest that we should think that the main leader here for the nature of the prompt emission should be synchrotron emission plus inverse Compton. Is it so? The answer is no. Probably you know it, because when you, let's say, take the theoretical expectation of having a, let's say, relatively compact region with probably a large magnetic field where particles are accelerated, you end up with the fact that the accelerated particles should release their energies through synchrotron over a time scale which is extremely small, orders of magnitude smaller than the dynamical time scale of the source. In turn, you should see a synchrotron spectrum, which is, let me use this word, a completely cooled spectrum. It means that in the low energy part, you should see a slope which is in photon index -3/2 or nu to the 1/2 in with nu. And when you compare this with the observation, you see a major violation, because you should see, in most cases, a spectrum which has this photon index at low energies. And when you measure the spectral slope of GRBs detected by, for instance, Fermi, both in short and long GRBs, you see that they are much harder. Possible solutions to this major problem, which is known since many years, have been proposed. For instance, in this work by Frédéric, but also some other works. Let's say what has been done was to consider how we can probably better refine the synchrotron emission mechanism and see if we can resolve this inconsistency. So for instance, accounting for inverse Compton cooling in klein machine regime, or let's say extremizing, if I can use this word, the physical condition of the source in order to, let's say, prevent electrons from cooling so fast, provided you can create these conditions. You can indeed find harder slopes and therefore become more consistent with the observed values. What happens is that, for instance, if you reduce the magnetic field of the emission region, you lower the cooling time scale of electrons, and therefore the cooling frequency that you see here appears in your energy band. Then you may happen to measure this break here, or to measure a single power, depending on the flux or the signal to noise that you have in the spectrum. This possible solution anticipated by Frédéric was, I guess, missing some direct evidences in the observations, which were found in the recent years, where, for instance, going back to analyze the brightest events in long gamma ray bursts and short ones, what we found preferentially in long gamma ray bursts is the fact that indeed the spectrum looks like synchrotron, because we found the presence of this break, which we can interpret as the cooling break, owing to the fact that below and above the break, the slopes that we measure in this burst as an example, but there are others, are indeed those predicted by synchrotron. We can do something more. We can, as you probably would suggest, we can fit directly a toy synchrotron emission model from, with some assumptions to the observations, from where instead of just deriving the observable, we derive directly the parameters of the emission region. And what we found here is that from this fit, for instance, the value of the magnetic field, provided you assume some radius for the emission region, is of the order of 1 Gauss, which is orders of magnitude smaller than the value that you expect for different reasons related to the jet power and the conditions that you should have there, provided that you find, okay. This most value of the magnetic field introduces on the one side, this result is reassuring. We can say that we have, at least for these events, a strong evidence that there is consistency with synchrotron. On the other side, the interpretation of this most value of the magnetic field poses other challenges. The main argument is the fact that if you keep the emission region, let's say, close to the, as it should be from the variability argument, close to the central engine, you should therefore have a quite large inverse Compton component, which could be observed already disturbing the, let's say, GeV emission, which is not indeed suggesting that much the presence of such a component. There are possible ways out, which I list here, which are related to the properties of the magnetic field in the region back of the shock, or we propose the possibility to substitute the particles which are emitting synchrotron radiation instead of electrons using protons. This is a possibility because the cooling time scale ratio of protons to electron scale is the mass ratio to the 5 power. And so it indeed produces with normal magnetic field values a cooling frequency as we observe it, but it opens other issues which we are still studying. Now, I try to move to the low redshift domain. Is it fine with the time? Okay. Where I would like to cover 2.5 topics. The first one is related to the latest discoveries of GRBs in the highest energy range. As I anticipated, starting in 2019, we started to observe with ground-based Cherenkov telescopes the emission at TeV energy of these sources. This is the list of events, and here is a plot showing their isotropic equivalent energy in gamma rays as a function of redshift. They are highlighted with stars. We have 4 detections, highly significant, and we have 1 detection, this one, which is only 3.5 sigma significant. The majority, let's say that 3 out of 4 or 4.5 events are, let's say, highly energetic events. 1 is down here, it's a low energy event, okay? So we are starting to have these 4 events. We cannot draw much conclusion from this, but it's a good start. The important point is, why do I place this topic in the low redshift universe? Probably is obvious to you, because we are in this case limited by the fact that we can observe TeV emission from these sources only close by, because at already redshift 1, you have that TeV photons are dramatically suppressed by the absorption of their emission of gamma ray photons through the interaction of the EBL light, okay? And therefore, there is a kind of horizon where we can observe them, which depends on different assumptions and also on the, let's say, spectrum of the EBL. But in general, you see that probably we cannot go beyond redshift 1.5 or 2. Let me just give you a couple of informations about these events of what we have observed so far. So here you see a light curve, flux as a function of time in different bands. The blue one is X-ray, and if you can see it, the green one is the magic observation, which pertains energies of the order of a few TeV, okay, up to a few TeV. The first thing you can see is that the shape of the TeV light curve is very similar to the X-ray one. And this is an indication of the fact that since this emission observed by magic is quite, starts at late times when the prompt emission is already finished, this is the first indication that this emission is produced where the afterglow emission, the X-ray emission is. And so it is afterglow emission. Something more, if we build up an SED at this epoch here, what we have is that this is the X-ray spectrum. This is the TeV spectrum as it was reconstructed. So this is the observed one when you deabsorb for the EBL absorption, this is the intrinsic one, okay? And this is a LAT observation. What you see is that this SED cannot be fitted by a single component, thus suggesting that what we are observing at higher energies, if this is the synchrotron component, is the synchrotron self-Compton peak of the emission. And this is quite informative on the properties of the source. There is another example I want to make, which is instead the opposite burst in the energetic distribution, because this is the low luminosity event we are dealing with. In terms of light curve behavior, we have a similar situation. You see the TV emission observed in this case by Hess is similar to the X-ray one. And when I say similar, I mean both in terms of temporal decay and luminosity, as you can see. However, when you build up the SED, the, let's say, conclusion we have maybe for this event is less robust. Because you see, for instance, the Hess collaboration tends to prefer a fit of the X-ray up to Hess SED with a single synchrotron component rather than with a synchrotron self-Compton component that is represented here with the blue model. We have been studying this burst, so we basically populated this light curve with other observations that were provided in the literature, and we added observations we acquired in the radio band, which is quite constraining for some properties of the burst, especially the density of the interstellar medium or the ratio between the energy and the density of the interstellar medium. Here is the result. This is the light curve. You see the X-ray light curve. You see the radio observations, which are shown here, and the optical ones. The burst is quite complicated, but we fitted it with, let me say, kind of reasonable state-of-the-art model, which includes all the dynamical and radiative properties that we expect from the afterglow emission. This is the result of our modeling of the SED. So we have the broadband SED that contains also lower energy data. This is the X-ray, this is the Hess emission. And by taking basically the fit of the light curve as a function of time and extrapolate and taking out the spectrum at the time of the Hess observation, we can fit quite nicely the SED with two components, with a synchrotron plus synchrotron self-Compton spectrum. I must say that there are many other notable things that we derive from this modeling, which I don't have time to go through. The only thing I want to say is that we tend to pretend, of course, probably we are biased, our interpretation for this burst being synchrotron self-Compton, what has observed, because there are also some intrinsic, to my knowledge, difficulties in interpreting the TV energy as synchrotron emission, because you would require to have one TV photon like the one observed here. For typical GRB parameters, you would require electrons to be accelerated at PV energies, which is orders of magnitude larger than the maximum energy you can acquire at shock acceleration by balancing basically energy gain and synchrotron losses. So this is more or less the situation. I think there will be other studies and possibly other events from where we can test and answer definitely this question: what is the origin of the TV emission observed by Cherenkov telescopes in GRBs? The future is hopefully brilliant with the development of the Cherenkov telescope array, which will provide better information, probably not, I dare to say, extremely orders of magnitude more events, but better characterization of their time evolution and spectral characteristics in the TV energy range, GV up to TV energy range. The second point I want to make about the low redshift is that, of course, as you know, we detect GRBs, short ones, we should detect in association with gravitational waves. This is a summary of what we learned from GRB 170817, gravitational wave 170817. We detected the gravitational wave signal, the thermal emission, the kilonova, and non-thermal components in the form of the GRB and the afterglow. There are many things that were learned from these events and many things we can do with future events, both concerning, let's say, multi-messenger studies or studying the properties of the size producing heavy elements, through the kilonova studies, the jet structure, or fundamental physics. What I want to say is what we should expect for the future. Now, the future is at the end of this year, starting in December this year, the gravitational wave interferometers will start again acquiring data. So what should we expect? I work on the electromagnetic side, so I would like to know how much I should work, of course, by new events. So the situation is the following. We tried to build up a model, or binary population synthesis model, which differently from those that appeared in the literature, goes a bit more into the physics of the sources. So we started from a binary population system BNS model, and we applied some physically motivated recipes to predict the electromagnetic emission in terms of kilonova and gamma ray bursts, both prompt and afterglow. Don't have the detail to explain what we did, but remind what I said at the beginning. Here, orientation effects are playing a major role, both on the gravitational wave emission, which is orientation dependent, and on the GRB itself, which is orientation dependent. What we obtain is the following. This is the BNS, let's say, formation rate as a function of redshift, which is increasing. We simulated the gravitational wave emission signal, and we applied the detection for the O4 run. And this is the cumulative detection rate as a function of redshift for HLDK in O4. When we go to see what are the chances of detecting the kilonova emission, assuming a relatively wide search instrument with the magnitude limit between 21 and 22, we find that there is a good chance, as for instance, Robert anticipated, of detecting in a larger fraction of gravitationally detected events the associated kilonova. It seems, however, that when we go to the non-thermal components, GRB and afterglow, at least in the initial part of the game, okay, when the gravitational wave alert is released, there are not that many great chances of detecting both the afterglow and the prompt. However, it's not so depressing because, of course, the game probably will go this way. Once you have the kilonova identification, you can shoot the best instruments you have to capture the afterglow emission. The prompt is gone, unfortunately, but the afterglow is promising. And by, let's say, modeling an ideal possible observational strategy which goes deeper both in the X-ray optical and radio band, we end up with good chances to detect at least one event with the kilonova and the afterglow associated in the next year or so. The reason for this difficulty is the fact that, as I said, orientation effects are important here. In fact, from this simulation, if we take out the majority of events which we could observe within the horizon of gravitational of O4, we end up that the majority of the events would be off-axis GRBs, which will be captured when they peak because the jet beaming angle becomes comparable to the viewing angle, which similarly to 170817 would happen at several hundred days after the GRB, the merger detection, the gravitational wave alert. Last two slides, really, if I may, is going to the even lower scale, which is a kind of provocative question, that is, what if a gamma ray burst happens very close to the Earth or to a planet with some kind of atmosphere similar to the Earth? This is a provocative question because I tell you the origin of this question. This is a question I've always been asked when making a presentation to popular audience or even when doing lectures to first year students. And at some point I said to myself, probably it's time to go deeper and try to study this question with a serious approach, because probably you're smiling a bit behind your mask. And indeed I was doing the same. This question is not unanswered. I mean, there were works in the past that tried to answer this problem and found very interesting results. The nice point is that at least for me, I'm obliged to explore a field which is completely unknown, where I don't understand much, which is that of chemistry and interaction of radiation with the atmosphere. It's stimulating, but I'm still really at the very beginning. So forgive me if I say something which is not correct. So what is the problem? The problem is that, of course, this argument doesn't consider all the mechanical effects that you can have by meteor bombing, okay? The idea is, let's study what is, let's say, what are the effects that highly energetic radiation can cause on the atmosphere of a planet. This has been studied by works by Mellot. There are a lot of works in the literature. And the main point is that if you have some high energy radiation, meaning X-rays, okay, that invest the layer of the ozone, the first effect is photodissociation of the ozone layer, which if the flux integrated in time, the fluence that arrives on the atmosphere is of the order of 10 to the 8 erg per square centimeter, you have 99% of depletion of the ozone layer. The side effect is that when ozone is destroyed, it recombines with nitrogen, producing dioxide and monoxide nitrogen. Monoxide nitrogen is then acting as a kind of shielding, preventing the sunlight or starlight to arrive to the surface of the planet. Therefore, it induces major cooling. Dioxide nitrogen precipitates in terms of acid rains. So these are the main two effects. The point is that, as you know, in the last 5 billion years, we had 5 major mass extinction events on the Earth. And the oldest one happened 450 million years ago. The Ordovician extinction, where probably very small stuff were destroyed, might have been caused by a transient, high energy transient. This is the question we try to answer. This problem was tackled in the literature, but what we wanted to do was to go a bit deeper. Now, introducing our better knowledge of GRBs and also including supernovae. So we build up a model where we basically consider high energy transients in terms of long GRBs, short GRBs, and supernovae, considering both their energetic properties and rate. Of course, you understand that they are different events. GRBs are extremely energetic, but rarer. Supernovae are less energetic, but they happen at a higher pace. And there is a trade-off effect with these, which should be included in this kind of study. The second thing is that we just didn't want to know if the Ordovician extinction could be caused by a GRB, which was already anticipated. We wanted to know how the regions in the galaxy, in the Milky Way, could have been evolving as a function of time over cosmic times, considering these lethal events altogether. So we built up a model for the Milky Way evolution based on the works by Nab and Stryker. And we also included some recipe for the planetary formation, rocky planetary formation, which is what we want to know from the works of Zachrison. These plots should summarize what we get. So here you see a kind of evolution, you can read it in this way, of the galactic habitable zone as a function of galactocentric radius. So this is a snapshot. Here is cosmic time evolving from all times up to now. And this plot is intuitively showing good regions where to live, which are green, and bad regions, which are red. The point is that from what I said at the beginning, for instance, the first point is that long gamma ray bursts here are the worst thing, because they are extremely energetic and they overcompensate the higher rate of supernovae and the lower energy that is released by short GRBs. So the driving point is the metallicity and star formation rate evolution within the galaxy. With this, let's say, model for the Milky Way evolution, we have that, for instance, if you take the epochs before 6 billion years ago, so cutting the region here, what you get is that the most favorable regions where a planet could survive such lethal events was in the outskirts of the galaxy. However, due to the fact, and this is induced by the fact that there was a prevalently small star formation rate, okay? However, in these regions, the metallicity as a consequence of the regions was small, and this prevented the higher formation of rocky planets. So it was safe, but low populated, we should say. As time goes by, you have this plum coming up because basically of the inside-out evolution of the cosmic star formation, the rise of the metallicity in the outer parts, which quenches basically the habitability because of the rise of lethal events in the form of GRBs. And we end up with the say, green valley that we found here, where the sun is more or less at the edge, where you have more favorable conditions and higher surface density of terrestrial planets. If you want, if you take a snapshot of the last 500 billion years, this is the curve showing the integrated effects of supernovae, short GRBs and long GRBs, as well as density of rocky planets around M and FGK stars. So the bottom line here is that this is very interesting. Now we are, this is a work that we started as a project, which has many other, let's say, objectives with a PhD student, Riccardo Spinelli at the University of Como. I go to my conclusions very briefly. I think I showed you that long and short GRBs as cosmic population are extremely informative because the key properties we can reconstruct from the current observation, which, by the way, improve as time goes by and we acquire more events, are indicative of the jet physical properties, for instance, the distribution of the energy and bulk velocity, and of the progenitor and the environment. GRBs as probes of the high redshift universe are extremely tantalizing. We need something which is able to detect them efficiently, localize and measure the redshift, and possibly then go to deeper studies. The prompt emission origin is, in my opinion, still an open subject, which needs to, let's say, understand a bit better what is happening. The low redshift range is full of many interesting things. Here is where we detect typically peculiar events, which oblige us to test deeply our theoretical models. We have learned that with the gravitational waves and associated GRB, we are learning that with very high energy events detection. And the last point is that long GRBs may have a role for the development of life on terrestrial planets, and now possibly also, let's say, over cosmic epochs, as we are trying to reconstruct, not only related to the Milky Way itself, or Milky Way toy model, as we did. Thank you.
Thank you, Giancarlo. Thank you for the nice talk. Thank you for the diversity of the topics we discussed. The last one was very special. So I suppose that there are any questions for Giancarlo?
Yeah, thanks for the nice talk. My question concerns precisely the last topic. I'm sure that before doing that work, you looked at the literature, which is quite important in that topic. And perhaps you have seen reviews on the galactic habitable zone with very funny results. Over the years, people have said that the inner galaxy is dangerous, then the outer galaxy is dangerous, then the whole galaxy is dangerous, then nothing is dangerous. So, and this of course reflects the fact that habitability is something which is very poorly defined. I don't know what, this is my question, in fact, what definition is for you of habitability. But for instance, when you mention catastrophes, you should also distinguish between life in the land and marine life.
Right.
And when we look in those, the statistics about those catastrophes, we see that in some cases they are similar. A lot of the organisms in the land disappeared and a lot also in the water. But I'm curious to know how you define the effect of a gamma ray burst. It affects the atmosphere, fine. But what about marine life? And how do you find habitability in general?
Yes, so thank you for the question. In fact, it's very important what you said, and forgive me if I wasn't clear on this topic. we took an approach which is really, really minimal. It is true that defining habitability is really complex because you may have different effects and different, let's say, parts of the biosphere which are affected by different mechanisms. First of all, as I said, here we are completely ignoring mechanical effects which can be induced by by impacts, for instance. And we simply define the habitability related to the percentage of ozone layer which can be destroyed on a planet which possess, by the way, the ozone layer. So it's a really, if you want, restrictive or focalized definition. To my knowledge, and I apologize because I'm a newbie to the field, what I understood is that radiation effects like those we are describing here, which are transient but extremely powerful, could induce a major effect because of the fact that you have climate changes on a time scale, according to the works of, I remember the works of Mellot and another one, I can't remember the first author, where basically you have a time scale of the order of 10 years over which you can have major changes in the temperature of the surface. Probably there is a survival of marine biota. On the other side, there could be a major effect on the surface because of precipitation of compounds produced by the recombination of ozone. To conclude, is not a full, complete description and definition of habitability or if you want, resilience. Okay, it's just focused on the high energy radiation. The nice effect, which is described in the literature, is the fact that of course, the part of the atmosphere which is bombed by this radiation is only one part of the atmosphere, but the high depletion of the ozone is so much that probably within a few years, there are simulations that say that there is a redistribution of the atmospheric, let's say, depletion all over the planet. So that's why people, I think, thought in the past that this effect could be inducing mass extinction, because all the planet would be interested, and at least for this effect, it would be catastrophic for the terrestrial biota and the plants, of course. I hope I answered to your. Okay. Thank you.
Thank you very much, Giancarlo, for your talk. About your last point about the perspectives for detecting new multi-messenger events. You have shown some predictions here. Of course, here, I guess, these are all the detectable events in terms of flux, but then there's a difficult question of the efficiency of the search for this counterpart, for instance, for the kilonova, taking into account, for instance, the size of the error box.
Yes.
So what is your view on this point? How do you estimate the current efficiency and the perspectives to improve it?
Okay, so probably it's more pertinent to this to answer your question if I show this plot here. Yes, you are right. So here the kilonova, let's say, identification is only based on the hypothesis that you go at a certain magnitude limit, but you're able to cover both, of course, small error regions or large ones, probably guided in the larger cases by some galaxy-targeted approach. So we didn't study in detail the strategy of, because we didn't want to assume any specific instrument where you have to account for the field of view and so forth. So the detection efficiency of 78%, for instance, kilonova, is just related to an instrument which we assume can cover somehow in some shots or targeted shots the error region, which can be quite large. Indeed, for the identification of the, for the gravitational wave signals, to my knowledge, there will be a larger fraction of events which will still have in the next run a relatively large location accuracy. Yes? Yes, please.
When you say this, you mean you are assuming that there is an instrument that they cover the error region entirely retro snapshot within a shorter enough amount of time?
Within a time scale typical of the evolution of the kilonova light curve. And so we assumed, so I don't have the plot. So we simulated the kilonova emission and we normalized the population kilonova emission in terms of shape to that of 2017 GFO. So roughly speaking, provided you can cover this within, I would say, 1 week, reasonably, with some specific search. I understand this is the major issue and of the next run. The identification, you mean for disentangling with other competing transients.
Thank you so much, Giancarlo. I really enjoyed the talk. Thank you very much.
Thank you.
I had a question about the 1908 29. Is this we're looking at the high energy emission from Hess, and your models seem to fit very exactly. And then on this,
this one, okay.
Yeah. And I was wondering if your models worked at different times for this burst as well. So I see that there's two plots on the left over here for two different time slices, I believe. And does your model work at multiple times, or is this?
Yes, definitely yes. So the model is a standard, let's say a standard. It's an afterglow model where you basically couple the dynamical evolution of the jet with the radiation properties by somehow adopting receives, which renormalize as function of time steps all the things that you have to do. And yes, indeed, as you can see, I forgot to sign here, but these two blue and red SED corresponds to different epochs, and they are exactly 2 points along the solid lines that you see here represented in the light curve. Okay, so I don't know if I got your point. Okay.
Just that the blue and red were different hours. That was my fault. Yeah.
Okay, thank you for the talk.
Thank you.
Like Mike, I really enjoyed it. I had a question about this this population that we discussed just earlier, the population model for the detections. You mentioned that that your model has a physically motivated approach.
Population model for binary systems. Sorry.
Exactly. Yeah, sorry.
I got confused. Okay.
And I was just wondering if you could give a bit more details on what your physical motivations are. And
okay.
These kind of models. You mentioned briefly the orientation.
Yes, I'll try.
Thank you.
Let me arrive to the slide because it guides my memory at least, because it's a quite complicated topic. Okay, so the first ingredient is here in simulating the binary neutron star systems. There are two approaches, and we took one, which is probably not so common. Instead of relying on, we discussed also in these days on binary population models, which derive the properties of the binaries based on recipes for the evolution of the system and so forth. We basically injected system by sampling a distribution of chirp mass and mass ratio, which is made consistent respectively with the posterior distribution of the chirp mass of the two gravitational wave events detected as binary neutron star merger, and the mass ratio distribution of galactic binaries hosting a neutron star. And this gives you quite nice constraint, which a posteriori we compared also with some of these population models, and we find overall good agreements. But in a way, sorry, it's technical, but we are a bit independent of the things you were showing to me that you find in one of these models. Then what we have is that we, let's say, evolve the system, and we consider only systems which have enough mass to produce a black hole, so above the maximum mass sustained by non-rotating system. And we have from the mass, let's say, budget, the amount of mass that goes in the disk, with some fitting formula that are derived by the works by Dietrich, no, I don't remember the name. Oh, okay, I can give you the reference. So we use fitting formulas derived by numerical simulation of the amount of power that you have in the jet and the amount of mass and distribution of velocity that you have in the kilonova. And so from these, we were able to have the initial conditions for computing respectively the kilonova light curve, emission as a function of time, and the gamma ray burst, because we have all the properties of the jet. Also, there we used a model for the formation, for the evolution of the jet within the ejecta and the acquisition of structure, and then the emission, which is based on the work by Giacomazzo and Salafia 2020 or 2019. Give me with names and remembering. So this is, and then we have, okay, so then we have the details of the prompt emission. The prompt emission, we assume prompt emission from a structured jet, where if you want, we didn't assume any dependence of the efficiency as a function of the angular distance from the axis, which is probably something that should be explored better. And for the afterglow, we use the same afterglow model that we use for 29A, so with forward reverse shock and synchrotron and inverse quantum cooling. Okay.
Just a small point for you in the German as well. 78% of kilonova counterparts are observed among the gravitational wave events for the next 04 run. This is what it means.
What we estimate, yes.
Observable. Yes.
Yeah.
Observable.
Observable. Detectable, let's say.
Detectable.
Detectable, sorry. Yeah, detectable. I should use this one.
So you have to assume that there is a question on the Zoom.
Yes, so there are some questions on Zoom, so please, Diego.
Yes, hi, Giancarlo. Thank you very much for this seminar. I have a question on this plot. I would have naively expected that the detection rate at a certain point would drop with distance because the events become too faint. But while you show that this remains more or less constant, could you explain the reason for that?
Sorry, Diego, probably I wasn't clear in explaining the plot. It's because it's a cumulative detection rate. So you count how many events you get below a given redshift, and when you level out, you have reached the horizon. So okay. Here you can read from here, for instance, that the expected horizon for gravitational wave detections is about 300 megaparsec. Yeah, that's it. So sorry I was too quick in this. If I may add a comment here to myself, which I forgot to say, probably you have noticed that independently from the numbers, there is a nice effect down here because you see, with respect to the other curves, which are more or less linearly increasing and then bending to the horizon, in the case of prompt emission, we have this turn up at very, very low distances. And this is due to the fact that in this model, we account not only for the emission of the jet, okay, but also for the fact that when the jet arrives to the surface of the star, it has deposited a fraction of its energy in the material of the star. And there is what is called the shock breakout, which probably is a region with a wider distribution in angle, which surrounds the jet. And this is the dim component, which you can most likely observe when you are off axis because you are not overshined by the jet emission itself. And in fact, it, let's say, introduces this bending, or if you want, excess with respect to the prompt emission, if you want, without this effect trend, which would go down linearly here.
Okay, there was another question by Zoom, please, Frederic. We don't hear you, Frederic. You seem to be unmuted, but we don't hear you.
Is it better now?
Yes, it's better.
Okay, sorry for that. So thank you, Giancarlo, for your seminar. It was very, very interesting. I have a question. I'm curious to know your opinion about cosmology, doing cosmology with GRBs that you haven't addressed today. You probably had no time for that, but okay, there are plenty of studies in the literature and using relations between observed parameters or derived parameters like RS', P, K ISO, L ISO, or other parameters. These relations are okay. It's very difficult, as you know, of course, because they of observational biases, strong observational biases. But there are also these relations are also shaped partially by physics, but they are scattered. The scattering is quite huge, and this limits the performance of these using GRBs for cosmology because they are hidden parameters, or we have to account for more detailed physics to standardize GRB. So my question is, what are the prospects, in your opinion, for this kind of studies in the next 10-15 years, and especially given a recent progress made on the GRB jet physics that you presented today? So is there any hope to have to standardize the GRBs enough, let's say, to reach the needed accuracy to have a new cosmological probe in the near future? What is your opinion on that?
Okay. Thank you, Frederic, for your question, which is a topic I didn't touch. So it's probably, I have a long answer to your question. I don't have any slide to explain the topic to the audience, I'm sorry, but in general, if you ask me about what you said, I perfectly agree with what you said. There are many observational biases, and the main limitation at the moment is the fact that at least for some of these distance indicators, we have a large scatter and we don't completely understand their origin. In addition to the fact that there are observational biases which we cannot completely as well reproduce or understand. So I would say that, okay, I can make it a personal answer if you want. With respect to many years ago, probably the situation is not so clear to me now. For the prospects, I think that probably the evolution of this field would benefit from both the acquisition of better characterization of the prompt emission properties, but also the understanding of what we see. Because, as I said, since we are not completely now still aware of what is the origin of the prompt emission, I think this also influences the fact that what we, for instance, draw in terms of correlations is just derived from the observations, and these are biased by the behavior of the detectors that we use to derive those. But the main point, in my opinion, is the fact that we have to face with the large scatter. And the large scatter, at least for some of this correlation, I think is hindering the fact that there is some other physics behind. So if we want to arrive ideally to have a distance indicator, probably we should arrive to the fact that we accept that gamma ray bursts, for instance, if they were, if they had a universal jet, okay, and most of their properties should be ascribable to their orientation, probably we would get closer to standardizing them. So understanding, I wasn't clear, but probably understanding the properties of the jet in terms of structure is a way also to, let's say, reduce some of the dispersion or uncertainty that we have in these correlations. But it needs much more discussion, if I may say. in my opinion, and investigation.
If there is no more question, if there is no more question, I think we should thank Giancarlo again. Thank you.